All right, so in this video, we're going to look at the different relationship between the different properties, and we'll have different equations that we can use to solve questions related to changes in pressure, temperature, volume, whatever it may be, depending on exactly what's happening with that gas sample. So to start, we'll look at Amundsen's law, and with it, I'll also mention just at the start, we're going to have the names of these ones, of these different laws. So in this case, the relationship between pressure and temperature, if we're assuming the volume of a sample is going to be constant. But the important thing isn't going to be remembering what is Amundsen's law in terms of what are the properties that it's relating. The important thing is just knowing if we're referring to pressure and temperature, how are those two going to be related if everything else is constant? I'm at least in this course not going to be asking you to define these different laws, but I may ask you what's the relationship between pressure and temperature, and we want to be able to identify that they're going to be directly related. So with it, we've got pressure divided by temperature is just going to be equal to a constant. So if we think about just an initial pressure divided by an initial temperature, that'll just be equal to K, or whatever that constant we want to use is. But if we also do pressure 2 divided by temperature 2, so we change those conditions and divide them, we'll also see, and again, we're assuming that the volume hasn't changed, we'll see that that still gives us the same constant value. So what we can do in that case is set the initial pressure divided by the initial temperature equal to the final pressure divided by the final temperature. And then those are going to be our equation essentially for this piece now. So if you look at the right here, we've got a graph in temperature on the x-axis with pressure on the y. And essentially what it's showing is if we took this volumetric flask, or this vessel, whatever it's going to be, and we have some gas sample and we cap it, so the volume of this gas isn't going to change because the gas just can't leave the flask. And then it's also just going to be a rigid container, so it's just not going to change the volume of it. So if we place it in ice versus room temperature versus boiling water, which is what we're doing as we go left to right, 273 Kelvin to 293 to 373, what we're going to see is, of course, the gas is then going to change its temperature accordingly. So if we let it sit in there for a while, the gas will eventually equal the temperature of the ice water. If we let it sit on the bench, it'll eventually equal room temperature, and the same thing with the boiling water. But again, because this volume's constant, what we're going to see is as the temperature increases from right to left to right, excuse me, we're going to see the pressure will as well. So you can see in this case, at about 273, we've got a pressure of about 1 atmosphere. Closer to 293, we've got a pressure of just under 1.1. And then when we heat it up all the way to 373 Kelvin, now we're at about 1.35 atmospheres. So we're just seeing as we change this temperature, and again, assuming we're keeping the volume constant, which we are in this case, the pressure is going to have to increase as well. And then with this equation, we'll see an example of it on the next slide. With this equation, though, just recognize that the temperature, and then this applies to any of these equations we're going to see, whenever we're looking at temperature in terms of the gases, anytime we plug temperature into our equation, and again, it doesn't matter which equation it is, the temperature's always got to be in Kelvin. So if we think about it in this case, if we had Celsius, we can have negative temperatures in Celsius. So we could have a gas sample that's at -5 degrees Celsius. But then if we plug that -5 in here, that means we would need a negative pressure, essentially, in order to get a positive value on the other side. And a negative pressure just isn't possible. We could have a negative difference in pressure, but the absolute pressure can't be negative. That means there would be less than nothing in that sample, which just isn't possible. So just recognize whenever we're plugging in temperature, it's always going to be in Kelvin. If we're looking at delta temperature, so just the change in temperature, in that case, Kelvin and degrees Celsius change at the same rate. So in that case, the change in temperature doesn't matter. But if we're looking at the absolute temperature, we always need it in Kelvin, because that's going to be the only scale that starts at 0 and only goes positive. Absolute 0 in Kelvin is just 0, whereas in Celsius, it's -273 degrees. So we just need to make sure we've got Kelvin there. So if we look at a practice question, the reason I should also mention, you might be familiar with this one, is if you've just had any sort of aerosolized can, so it's pretty much anything that you can spray something out of. Typically, there's going to be some sort of warning to either keep it from keep it within a certain temperature range or not heat it up a certain amount, because what's going to happen is as we heat it up, we increase that pressure. So you can actually kind of make a little sort of shrapnel bomb type of thing. If you heat up if you think about like Axe body spray, any type of deodorant like that, if you heat it up enough, of course, the container itself is going to be rigid, so the volume won't expand, which means the pressure is just going to build and build. Ultimately, it gets to a point where that can no longer handle that amount of pressure, just kind of explodes. So that's why with those types of cans, as we're seeing here, we want to make sure we don't heat them up too much. So in this case, a can of hairspray is used until it is empty, except for the propellant, which is isobutane gas. So that's just going to be a couple of carbons with some hydrogens around it. And with the first question here, I kind of already just answered that on the previous one. On the can is the warning, store only at temperatures below 120 degrees Fahrenheit or 48.8 degrees Celsius. Do not incinerate. And again, the reason for it is because we heat it up too much. It's going to become extremely pressurized, could potentially explode. And then the do not incinerate piece is going to be because that isobutane is going to be flammable. So it's going to be a combustible, flammable substance. So we just don't want to burn that as well. But then for the second piece, we can actually use that equation. We can figure out if the gas is initially at 24 degrees Celsius and a pressure of 360 kilopascals with a volume of 350 milliliters. And then we want to figure out if the can is left in a car that reaches 50 degrees Celsius on a hot day, what is the new pressure in this can? So take a moment thinking about the equation we just saw and see if you can kind of take this information, figure out what do we need to change, how can we plug this stuff in to ultimately figure out under these new conditions what the new pressure of that can is going to be. And with this one, again, we're thinking about the equation we just saw. So we've got P1 over T1 is equal to P2 over T2. So with a question like this, it may be useful to kind of list this information that you have. So initially, we've got T1 and P1. We've also got V1. And then if the can is left in a car that reaches 50 degrees Celsius, so that'll be our second temperature. And then ultimately, we're looking for P2. So with this one, it didn't explicitly state it. In some cases, it'll say, for that final sentence, it may say the volume of the can is unchanged, or the volume of the can is constant, the volume of the can stays 350 milliliters. So in some cases, it may explicitly give us information about that new volume. But in this case, if you think about just a can of hairspray, a can of pretty much anything, that's going to be a rigid container. So the volume of it isn't going to change as we heat it up or cool it down. So in this case, what we're doing is just assuming that volume stays at 350 milliliters. So for this question, it's kind of just extra information. Ultimately, we'll see, because we're going to see kind of the relationship between a bunch of these different properties. Ultimately, we'll be able to combine them into just one combined gas law equation. And ultimately, we would see if we have the volume the same on both sides, it cancels, and we can just remove that term. That's why we don't even need to plug it in here. But for this one, we need to focus on the pressure and the temperature. So with the pressure, it doesn't specify anything about the desired unit. So since we're starting in kilopascals, we can just stay in kilopascals. So what I would do is, let's see, 360 kilopascals. That'll be our P1. And then with the T1, 24 degrees. But remember, we want Celsius. So for this, just to limit the writing, I'm just going to do plus 273. Really, we'd have 273.15, but then based on sig figs, adding 24 degrees Celsius to it would just wind up with 0 digits after the decimal anyway. So then on the products, or not the product side, in this case, the final condition side, so P2 over T2, again, we're looking for that new pressure. So P2 is going to be what we're solving for. And then I'll also put this in parentheses just so we know the order of operations. So then the final pressure, again, same thing. We're going to have 50, but we need to convert it to Kelvin. So we'll do plus 273. And with this, just note the units with temperature are important, so we always need those in Kelvin. When we're looking at the other piece here in terms of pressure, we'll see the same thing when we have volume in the equations later on. The units for those properties, so volume or pressure, aren't important as long as they're the same thing on both sides. So in this case, since it didn't specify what the new pressure, what that unit should be, I would just keep it in kilopascals since that's what we have the initial pressure in. But if it asks for pressure in atmospheres or pressure in torr or whatever it may be, we could go through and solve for P2 in kilopascals and then make that conversion. Or you could convert 360 kilopascals to that desired unit and then just solve for P2 in that unit. How do I erase this? But with it, I'm just going to erase this so we can go to the next slide and see the answer. But again, I recommend making a table or just like I did, list what those property or these values represent in terms of P1 or T2, whatever it may be. But at this point, once we plug it in, we can divide the left-hand side, cross multiply by the temperature on the bottom of the right to get P2 by itself. And what we're going to see is we'll wind up with a new pressure of 390 kilopascals. And with it, we've got 2 sig figs in that initial pressure. So we can only have 2 sig figs in our final pressure. And that's why we're going to round to 390. I think if you plug it into your calculator, you get something like 391.5-ish. But since we only got 2 sig figs, we round that down just to 390. So if you want to practice with the learning check example at the bottom, feel free to pause it. I'm just going to go ahead and label what this stuff is. But again, we've got a sample of nitrogen, so N2, occupying 45 milliliters at this temperature and pressure. What pressure will it have if it's cooled to negative 73 degrees? So again, we've got T1 and P1, T2, and then we're looking for P2. But in this case, just note, we are given the volume again, V1, 45 milliliters. But at the end of this question, it says while the volume remains constant. So this is what I was referring to earlier. In this case, V1 and V2 are both going to be 45 milliliters. So what we could do is actually plug this into into our equation on both sides. We'll see ultimately it would wind up on the numerator along with pressure. So we really could have V1 times P1 over T1, and then the same thing on the right for 2. But since V1 is going to be the same on both sides, it just cancels, and that's why we don't even need to plug it in at all. But with this one, again, it's not asking for a specific pressure unit, so I would just solve for it in torr, since that's what we have the initial one in. But remember, we just have to convert these temperatures from Celsius to Kelvin. So instead of 27 degrees Celsius, we'd plug in 300 Kelvin. And instead of negative 73 degrees Celsius for T2, we would just plug in 200 Kelvin in that case. So we'd have 600 over 300 is equal to X over 200. So ultimately, as long as I can do this in my head properly, we should wind up with about 400 atmospheres, or 400 torr, excuse me. 400 atmospheres would be much, much greater. Yeah. All right. And then the second one we'll look at is now going to be the relationship between volume and temperature. And ultimately what we'll see is it's pretty much the exact same thing as with pressure and temperature. And that's why if you look at the graph here, essentially the only thing we've changed is instead of pressure on this side, now we just have volume here. But just note, even though this graph has the temperature axes in degrees Celsius, we can still graph it in degrees Celsius, but anytime we would plug these values into an equation, we still need to convert them to Kelvin. So we can graphically represent it in Celsius, so we have a better understanding of like what 0 degrees Celsius is. But when we're plugging them into the equations and stuff, we would still need to convert those to Kelvin. But with this example now, we're thinking about if the pressure remains the same, how is the volume going to change if the temperature is increased or decreased, or how is the temperature going to adjust if volume is changed? And just like with the pressure, we'll see volume and temperature are going to be directly related. So as we increase one of these, the other is going to increase as well, or as we decrease one, the other is going to have to decrease. And again, assuming that the pressure is constant. So with this example, if you look at the picture here, we can think of a few examples. So if you think about cooking bread, as we're heating it up, the bread rises. Going to be, again, because we're heating up that gas at constant pressure. So the gas then expands. Same thing with the hot air balloon. So if you think about it, you've got the little flame. I don't know exactly what they're burning in order to produce that flame, produce that heat, but they're burning that substance, getting the flame, heating up the gas within the balloon. And then if you think about the air itself, more or less going to stay constant pressure. So now that we're heating up that gas, it's just going to expand to a larger volume. Or if we cool it down, just the opposite, you would see it start to compress a little bit. So you'd actually see the gas become more dense. So the hot air balloon would start to decrease its elevation. And then with the ping pong balls here, if you think about down in the first floor of the 4000 building, there's the ping pong table in the student life or whatever it's called area. So if any of those balls got stepped on and just got damaged a little bit, kind of like we see on the left here, what you could do, you got to be careful, obviously, because if you use the lighter and get it too close to the ping pong ball, it's going to start to burn that plastic, which isn't something that you want to breathe in. But if you can hold the ping pong ball just a little bit above a lighter, the heat from the lighter is then, of course, going to heat up the gas within the ping pong ball. And similar to the hot air balloon, the pressure on the outside is going to be the same. So as we start to heat up that gas, it's going to expand to a larger volume. So it can actually kind of push out some of these little dents that we have in there. Like I said, of course, obviously, if you burn the ping pong ball, get that flame too close, it's going to damage it. It's going to expose you to some of the fumes of burning plastic, which is nasty. But if we can just heat up the gas without damaging the ball itself, we'll see that occur. All right. So now if we look at this one, going to be kind of the same idea. We want to think about, and especially because on a quiz or a test, it might not tell us that we're looking at volume and temperature. We may need to kind of figure that out. That's why it's so useful to list what these represent. So we've got a sample of carbon dioxide with a volume of 0.3 liters, V1, at a temperature of 10 degrees Celsius, T1. I don't know why I wrote C. That makes no sense for anything we're doing. So the 750 torr would just be P1. And we want to ultimately figure out what volume, so V2 is what we're looking for, if that gas is heated to 30 degrees and a pressure of 750 torr. But again, 750 torr is what we started with. So P1 and P2 are the same. They're just going to cancel. That's why we can essentially just not even worry about that piece. We're just focused on volume and temperature. So now we'll have 0.300 liters over 10 degrees Celsius. But again, we got to convert that to Kelvin. So I'm just going to do 283. If you want to do 283.15, whatever, it's the same thing. In terms of sig figs, it would really be 283, because if we added 273.15, we don't have any digits after the decimal here, so our addition can only go to the value that's least precise. So since this goes to just the ones place, our temperature has to do the same. And then on the right-hand side, we've got 303 Kelvin, because now we've got 30 degrees Celsius, so 273 plus 30, and we're looking for V2. So again, we'll do the division on the left, cross multiply by the 303 on the bottom. And with these units, again, just remember they have to match up for the volume or the temperature, or the volume or pressure, excuse me. So since we've got liters on the left, V2 is going to be liters. In this question, again, it doesn't specify a particular unit, so I would just keep it as liters. But if it asks for milliliters in particular, we could set it up exactly like we have here, get V2 in liters, and then convert to milliliters. Or we could, in that case, plug in 300 milliliters and just solve for our answer in milliliters. Either way, it's going to be the same thing. It's just whether you do the conversion before or after the actual calculation. But now that we've got all of this set up properly, now it's just the algebra. So I'll just erase it so we can go to the next slide. Just the algebra. and we'll get 0.321 liters. So again, when we look at our calculation, 3 sig figs in the volume, 3 sig figs in each of these temperature units. So we've got to have 3 sig figs in our final answer. But again, since we had volume V1 in liters, V2 also has to be in liters here. And with these ones, I didn't mention it for the previous one here. But here, always just make sure, like, just think about if your answer makes sense or not. So here, pressure and temperature were directly related. So as one increases, the other has to, or as one decreases, the other has to. So in this case, we went from 24 degrees Celsius up to 50 degrees Celsius. So we increase the temperature. We should see an increase in pressure. And that's what we did, 360 kilopascals up to 390. So even if we plugged something in incorrectly, we're still moving in the right direction. So it's a pretty good indicator that we're probably correct there. If we switched up these temperatures, so if we just switched up T1 and T2, then we would have gotten a pressure less than 360. So we can at least just think about if that value makes sense in terms of which direction should it move, just to see if we probably plugged everything in properly. And then the same thing here. In this case, we again increase the temperature 10 degrees up to 30 degrees Celsius. So the volume should also increase as well. And we went from 0.3 liters up to 0.32 liters, 321 liters. So again, it makes sense that we probably plugged everything in correctly there. So then with the check your learning one, if you want to practice that one again, just go ahead and do so, but it's going to be kind of the same idea. Sample of oxygen at 32.2 milliliters, 30 degrees Celsius, and 452 torr. We want to figure out what the new volume is going to be if it occupies, or if it has a temperature of negative 70 degrees Celsius and the same pressure. So again, this 452 torr is kind of just extra info. We don't need it. So this will be our left-hand side, our V1 and T1. We'll have 32.2 milliliters. (32.2 milliliters) over 303 Kelvin. And then with this one, since we're decreasing the temperature negative or 30 to negative 70, so in this case, we'll wind up with 203 Kelvin. Solving for V2 again. But in this case, since we're decreasing the temperature, we should see a decrease in the volume. And then if you look at these temperatures, 303, 203. So it's about 2 to 3 ratio here. So I would expect this to be about 2/3 of what we have here. So V2, just ballparking it, should be about 21, 22 something. So in the low 20s there. So let me erase this. And then when we actually go through and solve it, again, we just saw the setup, 21.6, right in the range of what I said there. And again, just looking at the temperature, looking at the pressure, going to have that same relationship. So since the pressure, or since the temperature decreased, excuse me, the volume had to decrease as well. All right, and now this one going to be a little bit of a different idea, but still using that same equation. We're just going to be solving for a different piece. So in this case, it's telling us that temperature is sometimes measured with a gas thermometer by observing the change in volume of the gas as the temperature changes at constant pressure. So in this case, you can kind of think of it as we're measuring the volume rather than the temperature. But then because of the relationship between temperature and volume at constant pressure, we can determine what that temperature is. And in this case, we're going to be using a hydrogen gas thermometer. So the gas that we're using is going to be hydrogen. And it's got a volume of 150 cubic centimeters when it's immersed in a mixture of ice and water at 0 degrees Celsius. So at 0 degrees Celsius, this gas sample occupies 150 milliliters, or 150 cubic centimeters. So this will be V1. Trying to squeeze it in there a little bit. That'll be T1. And then it tells us when immersed in boiling liquid ammonia, the volume of hydrogen at the same pressure is 131.7 centimeters V2. What is the temperature of boiling ammonia on the Kelvin and Celsius scales. So again, it's the same idea. We're just going to be, in this case, solving for temperature. But we've got 150.0 cubic centimeters. And then again, we still want temperature in Kelvin, so that's 0. We're just going to convert to 273.15. And in this case, I am going to include the 0.15 since this temperature is 0.00. And then ultimately, we're looking for T2. So we'll be solving for the denominator. We've got a second volume of 131.7. And that's centimeters cubed again. So again, with these ones, just look again, volume on the top is the same unit. That's why this works. If we had centimeters cubed and meters cubed, we would need to convert one of those to match the other. But now that we've got the setup, we can do the division on the left, cross multiply by T2, and then ultimately just divide by this on the right. So it's just a little bit of algebra there, or you can cross multiply both sides, then divide by 150 on both. Either way, just the algebra, you wind up at the same spot. But with this one, what we're going to see is if we solve for the temperature, initially this temperature is going to be in Kelvin, but we also need to get it in Celsius. So we're first going to solve for Kelvin, and then in order to get it to Celsius, we'll just subtract that 273 to make that unit conversion. So now if we look here again, same thing we had set up, do the division, cross multiply, divide again. Ultimately, we'll get a new temperature of 239.8 Kelvin. So again, we got 4 sig figs in the volumes here, 5 in the temperature, but now that we're doing division, we have to go fewest overall. So that's why we've got 4 in the temperature there. So 239.8 Kelvin. So before we even convert to Celsius, we can think to see if that makes sense or not. And it should make sense because we're decreasing the volume in this case. So 150 cubic centimeters down to 131.7. So we should see the temperature decrease as well. 239.8, definitely less than 273. So that makes sense. Likely plugged everything in correctly. And then the final piece now, we're converting to Celsius because we want it in both temperature units. So we're just going to subtract 273.15 from it. But again, we've got 1 digit after the decimal here. We had 2 in the Celsius Kelvin conversion unit. But since this only had 1 digit after the decimal and we're subtracting, our final answer can only have 1 digit after the decimal. So we should get negative 33.4 degrees Celsius there. All right, and then with the check your learning, I'm not going to work through that one, but same idea. This 1.1 atmospheres, again, it's just extra information since it stays constant. So all we're looking at is T1 and T2. And actually, it doesn't really matter which one's T1 or T2. You just want to recognize this 405 milliliters goes with the 298 Kelvin. So these will be on one side of our equation. And for this one, we already have Kelvin, so we don't even need to convert anything. We'll have 405 milliliters over 298 is equal to X over 467. So again, we'll just need to go through like we did here, do a little algebra and solve. And ultimately, we'll see 635 milliliters will be the new volume. And again, that makes sense because at 467 Kelvin, much higher temperature than 298 Kelvin. So that sample, since it's constant pressure, 1.1 atmosphere, should occupy a larger volume than what we had here. So 635 definitely larger than 405. So again, it's an indicator that we probably set up that equation correctly. All right, and then the next one we'll look at Boyle's law. So now if we're thinking about a constant temperature, what is the relationship between pressure and volume? And what we'll see in this case is that they're going to be inversely related. So whereas the other ones we had like volume over temperature or pressure over temperature because they were directly related. As one increased, the other increased. Now what we'll see is that since pressure and volume are going to be inversely related, as one goes up, the other goes down, what we'll see is that they're going to be multiplying. So we'll have something like P1 V1 is equal to P2 times V2. But that's also why if you look at the graph here, volume and pressure, you'll see we've got a curve. But the general trend, as we increase pressure, volume decreases. Or as we increase volume, pressure decreases. So it doesn't really matter how you think about it, but as one goes up, the other is going to go down. But then because of that relationship equaling to just a constant K, what we can do is do the inverse of pressure, and then the slope is just equal to that constant. But then because of that, we get a straight line in this case when we've got the inverse of pressure here. And then also with this inverse graph, just think about 1 over pressure. So as pressure itself gets larger, our denominator gets larger, so the value would get smaller. So in this case, with the inverse pressure, the left-hand side, so this point here, would actually be our highest pressure. So it would match up with that one. This would be our lowest pressure, would match up with that one. So the axes here are just a little bit backwards because we're looking at the inverse. So it's really highest pressure on the left, lowest pressure on the right there. But with that, I didn't mention it in the previous slides, but the kind of little squiggly sort of fish looking thing is just telling us the relationship between. So we need a constant in order to actually make these equal to each other. But this is just saying as pressure increases, essentially just saying pressure and volume are inversely related, while temperature and amount of gas are constant. And that's why we just wind up for Boyle's law with the equation at the bottom here. But if we look at this one quick, essentially what we have, P1 over V1, or P1 times V1, excuse me. If we put just over T1 and over T2, it's kind of just taking the previous two things we saw and combining them. It's just in this case, temperature, and then we'll see amount of gas, N, moles, is fixed, is constant, is why we essentially can just remove this piece. So with Boyle's law, that's why we're only focused on pressure and volume. The same thing with the previous ones. It's just depending on the two properties we're looking at, that third piece can just be held constant, and is why we can just essentially remove it. We don't really even need that information because it's going to cancel left versus right. Oops. And with Boyle's law, with a lot of these, you may be familiar with them. So if we think about like tires during the winter, you may see your car tires seem flat in the winter because as the temperature goes down, the gas in the tires are going to become cooler as well. So they're going to occupy less space, or they're going to give us less pressure, depending on exactly how you want to think about it. But these are also going to be important in terms of course, like hot air balloons and things like that. But in terms of scuba diving, there's what's known as the bends. What's going on here? Whoops. So if you think about the human body, as you go scuba diving, more or less going to stay at the same temperature. You may slightly increase or decrease temperature as you start to work harder, or as you go into slightly cooler water. I guess the temperature could fluctuate very, very minorly. But the internal body temperature more or less going to stay pretty much the same. So with the gases that are dissolved in the body, or in anything really, if we think about how those are going to change with the changing sea level, as we go further and further down into the water, we're going to have more water above us. So essentially just the pressure from that water is going to increase. So if we're thinking about a gas sample, the volume of it would decrease. But then as a diver then returns up to the surface, the opposite occurs. Those gases are then going to expand. So what can happen is if a diver dives too deeply and then returns too quickly, they can actually wind up with the bends, which is essentially just the gas inside their blood vessels basically expanding. And then gas itself, gas bubbles in the blood, is going to be a terrible thing that can affect, pretty much kill you. So that's why with the diving, if you're depending on the depth that you're going, you may not really even need to consider it at all. So if you're just doing like a simple shallow dive, not really anything to worry about. But if you do a much deeper dive, there's going to be kind of a protocol that you use in terms of returning to the surface, so that as you're returning, the gases don't expand too quickly and you don't run into that issue. With the bends itself, the exact like biological response and how that all occurs, I'm not super familiar with, but it's just going to be because the gas in the blood can then expand with this decrease in pressure. And then those bubbles in the blood can cause different issues. But then looking at the examples here, this final one, if you think about soda, again, we're thinking about pressure and volume. So if you had soda and you open it up, you kind of hear that fizz, you hear the gas escaping. And the reason for it is because now we're decreasing the pressure. By opening that can, we're decreasing the pressure. So we're then allowing that gas to then expand to much larger volumes. And then with it, we'll see when we talk about solutions, gases are also impacted, their solubility, I should say, is impacted by pressure. So when we decrease the pressure as well, it decreases the amount of gas that can stay dissolved. So there's kind of a couple different factors in there. But part of the reason is going to be due to that decrease in pressure, allowing that carbonation essentially to escape. So if you want to practice with this one, we've got a sample of gas, and then on the right-hand side is just figure 9.13. So it's got a volume of 15 milliliters and a pressure of 13 psi, so pounds per square inch. And then you can see the data from several other points as we change the volume or the pressure, how those get adjusted. Okay, so with this, might be a little pause in the video just because I got interrupted for a second, but I forgot exactly what I was saying. But with this one, we've got a graph showing the pressure and the volume. We've got a graph showing the inverse pressure versus volume, so a little bit different than the one that we saw before, but it doesn't really matter. If you think about it, if we've got a straight line for one of these being inverse, we can just flip the axes, so it doesn't really matter. What we're looking at there, of course, what the slope represents is a little different, but ultimately same kind of idea here. And then we also want to use Boyle's law to determine the pressure of the gas at 7.5 milliliters. So again, we're assuming constant temperature. So as the pressure and the volume change, we'll see that inverse relationship. As one goes up, the other's going to go down. That's why we've got the curve and just the pressure versus volume graph. So we want to use all three of these different examples or three different methods to, in some case, estimate, or in the case of the equation, calculate the pressure of this gas at that new volume. So if you want to take a moment to kind of work through that, the first two, we're just going to kind of look at the graph, find 7.5 milliliters and eyeball it. But then the third one, we can actually use that equation because we've got V1 and P1, we've got V2, so we're just solving for P2 there. So if you want to go through on those on your own, just pause the video. Otherwise, I'll just kind of click through. But for the first one, we're using that pressure versus volume graph. So if we want to get the pressure at 7.5 milliliters, we've got to kind of eyeball where 7.5 milliliters is. So we can go just directly in the middle of 5 and 10, and then just kind of go up from there. And with this one, I'm looking at maybe 27 psi, and that's actually what they got here. Whereas when we do the same thing for the inverse pressure versus volume, now we've got a straight line. It's a little bit easier to do. But in this case, 7.5 milliliters go up to here, and that's going to be, how many lines do we have? 1, 2, 3, 4, 5. So we've got 5 lines in between every 0.02. So that means every 0.02 divided by 5, each of these lines really represents 0.004. So if we go up from 7.5 till we hit that line, I'm going to say that's about I'm going to say that's pretty much right on the line below 0.04. So that's going to be 0.036. But again, that's going to be the inverse. So if we've got 1 divided by 0.036, that's going to be how we actually get the new pressure. And maybe 1.04, somewhere around there. But either way, we're going to be estimating the pressure. I got about 27 psi again from the textbook answer. They're getting about 26. But again, this isn't going to be precise because we're estimating based on the graph here. And with it, really, I can't even tell for certain just because I'm using the mouse to try to draw that line. But it's going to be the same idea. It's just in this case, we've got to represent 1 over pressure with the y-axis. So when we're actually solving for the pressure, we've got to divide just to actually get there. But then with the calculation one, we can actually plug in those values, see what it's going to be. And again, we've got P1 and V1, so 13 psi and 15 milliliters. We've got V2, 7.5 milliliters. So that's why we're just solving for P2 in this case. And we'll get 26 psi there. And remember, PSI is just pounds per square inch. So it's just a different pressure unit. But in this case, since it didn't specify for anyone in particular, we can just keep it as PSI. And then with it, it also asks us to comment on the likely accuracy of each method. I would say, when we're looking at the graphs, in this case, it's a little tough just because like it's an image on a slideshow. But typically, I would say the inverse graph is going to be a little bit easier to kind of work with just because it's a straight line. It's a little bit easier to estimate where that point's really going to be. And that's why they actually got a closer answer to what it really is in that case. Whereas the curve, it's a little bit more of a estimation. So it's just going to be a little bit more inaccurate. And again, neither of them is going to be perfect because either way, we're trying our best to kind of estimate where that point is on this line. Whereas the Boyle's law equation allows us to more precisely calculate what that value is going to be. Yeah, all right. And then this is a good point actually just to mention at the end. So they kind of do the same thing. A is more accurate, or more inaccurate, I should say, rather, than B or C. And then the calculation will be as accurate as the equation and measurements allow. So if we have good data, the straight line and the equation essentially going to work reasonably similarly. But of course, if we've got pretty poor data and then we plug it into Boyle's law, that data is not going to be accurate. So our final answer is just not going to be accurate. So in this case with Boyle's law, we're assuming that the pressure and the volumes were measured correctly or reasonably correctly. Because of course, if we've got poor data, it doesn't really matter if we do the calculation properly. And then with Boyle's law, so pressure and volume, you think about breathing in, just taking breaths really. That's going to be an example of Boyle's law. So when you're taking a breath, you think about you're not really like sucking in air in the sense that you're actively like forcing in air yourself. What's occurring is just the change in volume, change in pressure. So when you breathe in, you'll see the diaphragm contracts, pulls down, allows the excuse me. There, excuse me. But like I was saying, when you breathe in, your diaphragm contracts, essentially making the volume here in your lungs larger. So if we think about Boyle's law, increased volume means a decrease in pressure. So a decrease in pressure, we're going to see air flows from high pressure to low pressure. So if we've got a decrease in pressure in the lungs, that means we're going to have air being forced in that direction. But now when we breathe out, what's occurring is just the opposite. Now the diaphragm is relaxing, so it's decreasing the amount of volume here. So now that we're decreasing the volume, we wind up with a higher pressure in the lungs than we do outside. So now in this case, the air is still flowing from high pressure to low pressure. It's just we're essentially switching which is high pressure. So now we've got it in the lungs that forces the air out. So again, this is just going to be Boyle's law, just thinking about if the lungs are increasing or decreasing in volume, and then remembering that air is going to flow from high pressure to low pressure. So if you think about meteorology, the weather systems are going to move from high pressure to low pressure. You can essentially think about with the low pressure, there's less air there. So the high pressure is going to kind of flow in that direction to kind of fill it out, try to even it out. It's the same idea here, just on obviously a much, much smaller scale in terms of the amount of space, amount of volume that we're actually looking at. All right. And how many more do we got of these? Okay, so we won't look at all of these. We'll get to the ideal gas law. Okay. So now Avogadro's law, similar to Avogadro's number, is just looking at the amount of gas. So in this case, the volume of a gas at constant temperature, at constant pressure, is going to be directly proportional to the number of moles of gas. So this is going to be an important piece, especially when we look at the ideal gas law coming up. But essentially what this means is if we've got equal amount of moles of gas, doesn't matter what that gas is, if it's under the same conditions, it'll occupy the same amount of space. So if we look at a reaction like we see here, so hydrogen gas plus oxygen gas going to water vapor. When we look at the stoichiometry, 2 moles of hydrogen for every 1 mole of oxygen for every 2 moles of water. Because we've got these different coefficients here, we've got twice as many moles of hydrogen as we do water, or do oxygen, excuse me. So if we had these two samples separate initially, if we had them in some reaction vessel, separate reaction vessels, but same temperature, same pressure, the hydrogen, since it's got twice as many moles, is going to occupy twice the amount of space. But then what's going to be kind of unique is when we have these combined, if we don't change the pressure, the volume at all, or pressure or temperature, excuse me, the volume of this water vapor would be the exact same volume as the hydrogen, even though we're also now adding in the oxygen. Since we're still only getting 2 moles, we have the same amount of moles of the hydrogen, so the volume here would be the same. That's why we've got 2 volumes, and 1 volume. It's just looking at the molar ratio there. And with it, we often say, or we'll talk about later on actually, 1 mole of gas is often referred to as 22.4 liters of gas. And that's going to be true for any substance, but that's going to be at a specific temperature and pressure. So that's going to be standard temperature and pressure. But again, if we've got any constant temperature and pressure, the amount of space that gas takes up is just going to be directly related to the amount of gas, the amount of moles. So with it, we can now take it, and actually if we wanted to put an equation here, you can see volume is equal to some constant times the amount of moles. So if we wanted to, whoops, let me get the pen back. If we wanted to make it a similar equation to what we saw for the previous ones. Ooh, doing vanishing pen for some reason is not what I want. We could have V1 over N1, where N is just moles of gas, over or equal to V2 times N2. So just like the previous laws, we could just focus on these two. And again, the reason we don't have anything for temperature or pressure in this equation now is just because those are constant. So T1 and T2 would be the same. Those would ultimately cancel. P1 and P2 would be the same. Those would ultimately cancel. So that's why we're just looking at volume and moles of gas here. But with this, and we kind of already saw it on the previous slide when I went ahead moments ago, but what we can do now, and I mentioned it earlier, is we can take all of these different laws, all of these different equations, and just plug them into one giant equation. So P1 V1 over N1 T1. So the pressure times the volume divided by the moles of gas and the temperature. And again, temperature still has to be in Kelvin. Moles is just moles, and then pressure and volume, the units don't matter as long as it's the same thing for pressure and volume on both sides. But this equation is the same thing we've been looking at for the previous ones. Now it's showing all 4 of those variables on both sides, whereas with the previous ones, for Avogadro's law, temperature and pressure were the same. So P1 and P2 canceled. Could remove that. T1 and T2 canceled. Could remove those. So we just had V over N. So this combined gas law we could still use for all of those previous types of questions. It's just when any of those quantities stay constant, they stay the same. And then I should also mention, even if they don't give us a specific value, so in some of those questions it told us the pressure was 600 torr and it stayed at 600 torr. So we could plug in 600 on both sides and it would cancel. If we wanted to use this equation, but it didn't give us a specific value for one of those properties, but just said it was constant, we could make up any number we want for that property and just keep it the same on both sides. And we'll see a couple examples of how we can use this equation. But now it's just essentially looking at if all of these substances or all of these properties were to change for a given sample. If 3 of them changed, but 1 of them stayed the same, we could just remove that piece from it still. So looking at the question we have here, and now I would definitely recommend you label what each of these pieces represent. But when filled with air, a typical scuba tank with a volume of 13.2 liters. So V1 has a pressure of 153 atmospheres P1. If the water temperature is 27 degrees, how many liters of air will such a tank provide to divers' lungs at a depth of approximately 7 feet if the pressure is 3.31 atmospheres? So we've got P2, we've got T1. All right, and with this one in particular, this might not have actually been the best question to start with, just because we will have to make some assumptions. But you'll notice we don't have anything about the amount of gas of the moles. So what we'll say is N1 is equal to N2. So with our combined gas law, we just won't need to plug in moles of gas anywhere. So we can just focus on pressure, volume, and temperature. And then if we go back to this last sentence, how many liters of air will such a tank provide to a diver's lungs at the depth of 70 feet where the pressure is 3.13? So we're ultimately going to be looking for V2. So we've got V1, we're looking for V2. We've got P1, we've got P2. We've got T1, we're missing T2 though. So what this is telling us is the water temperature is 27 degrees. So the assumption we've got to make is that the second temperature is just going to be the regular body temperature. So that would have to be given to us or provided to us in another piece of information. I don't expect you to memorize that. Typically it's around 37, 38 degrees. I can't remember. It's going to be on the next slide when we see how it's set up. But now when we, oops, I keep clicking the wrong annotate button. Now when we look at our equation, we'll have P1, B1 over T1. And then we'll have the same thing on the right-hand side. And again, the reason we can remove moles is just because N1 and N2 are going to be the same, so it'll be just canceling. But the only thing we're kind of missing is T2. So we would just need to know what the regular, or assume what the regular body temperature is going to be. So when we look at this, let me erase it here. So it tells us letting 1 represent the air in the scuba tank and 2 represent the air in the lungs. So that's going to be like P1, V1. That 1 is going to be the air in the tank. 2 will be the air in the lungs. And noting that the body temperature is 37 degrees C. So that's, like I was saying, that's the kind of the piece that looks like we're missing. So P1, V1 on top, just the initial pressure and volume, 13.2 liters, 153 atmospheres. And then T1, we don't want to plug in 27 degrees C. We still need to convert to Kelvin. So that's why we've got 300 Kelvin. So this is our initial set of conditions when it's in the tank. Now this is going to be our conditions after the diver has kind of breathed in that air. So we've gotten the new pressure explicitly given to us. And again, we've got to assume that the body temperature is just going to be regular body temperature, 37 degrees Celsius. But again, we'll convert that to Kelvin, so 310. And then V2 is just the piece that we're missing. So we could go through and just do the algebra, isolate V2 by itself. So ultimately, you could do this entire left-hand side, multiply by 310, divide by 3.13, just to get V2 by itself. And then with this, we're going to see that the volume in the lungs then is going to be 667 liters. And with it, we can think about if that makes sense at all. Because if we think about the temperatures, 300 Kelvin versus 310 Kelvin, that's going to have a minor effect. We are heating it up slightly. But the major piece here is the pressure in the tank goes from 153 atmospheres down to 3 atmospheres. So it decreases by about 50 times. So it makes sense that the volume is going to increase a whole bunch. So 667 is a reasonable number. So we can, again, just check to make sure if that value even makes a little bit of sense or not. And of course, the 667 liters, a person obviously isn't going to breathe in the entire tank of oxygen, the entire tank of compressed air at one time. So that's going to be used throughout the dive. Of course, if somebody was then to ingest all of or inhale all of the air at that point, obviously not going to be a thing that they would probably survive. And with that, anytime you work with these compressed types of air tanks, so scuba diving, obviously there's a whole bunch of other things to consider, like we mentioned, the bends, but with these tanks, since they are compressed air, there's a whole bunch of air at high pressure. So whenever in the future, if you ever wind up working with these, whether it's in a lab environment or any other capacity, if you're working with these indoors, make sure that you've got some degree of airflow, a window open, a vent, door open, whatever it may be, because with these tanks, they're generally pretty durable. But if you think about a tank full of nitrogen, for instance, nitrogen, the largest component of the atmosphere, and it's a relatively inert gas, so it doesn't really react with too much. But if we had a tank like nitrogen in a tiny room, and then something went wrong with that tank, it fell over, it broke, and then just expelled all of that air at once. You think about it, there's a ton of air in here, 667 liters, and that's at 3 atmospheres of pressure. So if we're open, we do this at just atmospheric pressure, 1 atmosphere, that volume is going to be 3 times greater still. So if you have one of these tanks malfunction and it falls over, breaks, and releases that gas, it's going to release a huge volume of gas. And essentially what it can do is displace the oxygen in the room, depending on what gas it is and how much of it's left. So that's why you always got to make sure that you've got proper airflow whenever you're working with those types of compressed air tanks. All right, so with the next one, a sample of ammonia is found to occupy 0.25 liters under laboratory conditions of 27 degrees Celsius and 8.85 atmospheres. Find the volume of this sample. So again, with it, we're just looking to see what we have, V1, T1, P1. Of course, this really got to go to Kelvin, so we'll have 300 Kelvin. And then we've got T2, so just 273 Kelvin. And P2. So when we look at our equation, V1, P1 over T1, we're missing V2. Find the volume, so that's the piece that we're going for. But we've identified all of these other variables. So at that point, all we need to do is plug them in. We can multiply V1 and P1, divide by T1, and then isolate V2 by itself on the other side, just like we did for the previous one. Oops. And that's why I always recommend either setting up a table or just in the word problem like I just showed there, just listing what those are so we can see what information we know we have, what are we looking for, what are we missing, so we can make sure that we're solving for the correct piece. Because in this case, again, we know the equation that we're using is the combined gas law, but in other instances, it might just be a mix of all of those different types of questions we've seen so far. And the combined gas law would work for all of those. So if we wanted to use that and then just plug in values, see what we're missing, see what cancels, that always works. But this we can at least make sure we've got the information we need. We make sure that we're representing everything properly. All right, and with this one, let's see, do I want to start this at all? We'll look at one of these types of questions. So that was the combined gas law previously, where we can see one sample of gas, just how is it going to change as we change some or all of those different properties. But now what we can do is kind of take all of those and combine them into a single equation where we're only looking at a sample of gas under one set of conditions. So again, volume is related to the inverse of pressure, volume is related to the temperature, volume is related to the amount of gas. So if we take all of those and combine them, we wind up with something like this. So volume is related to the amount of gas times the temperature divided by the pressure. But again, we've got a relationship here. In order to make it an equation, we need some sort of constant. And what we'll see is that constant is just going to be represented by R, just known as the gas constant. So this is one form of the equation. Volume is equal to the gas constant times moles of gas times temperature divided by pressure. The more common version of this is just to multiply both sides by pressure, just so we have, if we get rid of that fraction essentially. So pressure times volume is equal to the moles of gas times that gas constant times temperature. And with this, again, temperature always has to be in Kelvin. Moles is always just going to be moles, but pressure and volume can be different units, can be atmospheres for pressure, millimeters of mercury, torr, bar, kilopascals, whatever. Same thing with volume. We could have milliliters, we could have liters, we could have a whole bunch of different units. So depending on what we have for pressure and volume, that determines the exact gas constant that we use. So there's a different R value depending on what pressure units we have. Essentially, they're the same. It's just unit conversions basically to give us these different numbers. But in order for that equation to work, we need to have the units match up. So if we go back here for a second, actually, let me do this. Insert text box. So if we think about the units here, so PV is equal to nRT. So if we think about pressure, we could have that in atmospheres. And if we think about volume, we could have that in liters. And then on the right-hand side, we'll have moles. And then I'm just going to use R. Oops, I didn't want it to give the, for now as the gas constant. And then temperature, we always need in Kelvin. So if we think about rearranging this to solve for R is equal to atmosphere times liter. And then we're going to divide this whole side by mole and by Kelvin. So what we'll see is the units for R that we're going to use most frequently are going to be atmosphere times liter, or I usually say liter atmosphere on top. But we'll have the pressure and the volume units multiplied on top, divided by mole and Kelvin on the bottom. And that's why if you look at these units here, we have mole and Kelvin on the bottom in each case. The only thing that's different is what unit for pressure and volume do we have. In some cases, you can see that they actually combine to give joule or calorie. But liter atmosphere per mole Kelvin is going to be our most common R value. But if we had a pressure in torr instead of atmospheres, we would want to use 62.36. If we had meters cubed and pascals, we could use 8.314, same thing as joules. So depending on what pressure and volume units we have, we may use a different R value. With these though, again, just like most of the stuff that comes in these types of tables, don't memorize it. I don't think that's useful at all. But again, we're just going to need to make sure that the units match up. Typically, we will use the top one there, liter atmosphere per mole Kelvin. But in some cases, we may have different units. We may have to use a different R value. So to look at just one practice one here, methane, and I should also mention, the reason we call it the ideal gas law is because we've got pressure, volume, moles, and temperature along with that gas constant. But nowhere in this equation is there a spot for us to plug in information about what type of gas it is. And because of that, that's why we're calling it the ideal gas law. We're assuming that all of these gases are going to behave ideally, which we'll go into a little bit later in the chapter. But with that ideal behavior, that means all of the gases are going to be the same. So it doesn't matter for this equation. If it's methane, if it's oxygen, nitrogen, whatever, the equation is going to work just the same. And with these ones, we're thinking about, do we use the ideal gas law? Do we use some version of the combined gas law? The way that we can determine that is by thinking about, do we have information about two sets of conditions? That'll be the combined gas law showing how the pressure, the volume, the temperature are changing. Or are we just looking at a sample under one set of conditions? So in this case, methane, CH4, is considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could be replaced by 655 grams of methane. What is the volume of this methane at 25 degrees Celsius and 745 torr? So with this one, we're going to need a little bit of extra info in terms of the conversions here. So just to go through it, firstly, the way that I would approach this is we've got mass, but we need moles. So we're going to have to convert that. And then we've got temperature, we've got pressure, we've also got volume. But this is going to be the volume of gasoline. So we're not going to use that value at all because we're looking for the volume of the methane. So this is going to be the piece we're solving for. So if we think about PV is equal to nRT. In this case, we've got the pressure. We're looking for volume. We can solve for moles because we've got the mass. We know what the substance is. Gas constant's always going to be given. Temperature we have. We just have to make sure that the units match up. So with the pressure, 745 torr. If you don't remember, 1 atmosphere is equal to 760 torr. So if we want to get this in atmospheres just to make the R value that we're typically going to use work, we could do 745 divided by 760. And this means we'll have 0.980. So again, we're just dividing by 760 in order to convert this to atmosphere because there's 760 torr in 1 atmosphere. Then we'll have the temperature, got to convert to Kelvin. So we'll have 298 Kelvin. Volume's what we're looking for, and then we have to convert this mass into moles. So we've got 655 grams. I'm just going to keep it simple and just do 16, just because it's 12.01 for carbon, 4.032 for hydrogen. So it'll really be like 16.04. But with it, that'll give us, so we don't want mass, we want moles, N. And when we divide by the molar mass of just over 16, what we'll see is in this many grams of methane, there'll be 40.8 moles. So now when we look at this equation, again, we're solving for volume. So we can really divide both sides by pressure. And we'll get volume is equal to, whoops, let me get that pen back, 40.8 moles. R is going to be 0.08206. Let me make that better so it's clear that that's an 8. 0.8206. And then again, the units for this are going to be liter, atmosphere. And that's why we had to make the conversion previously. We couldn't just plug in the pressure, couldn't plug in that just as it was, because the units wouldn't work. So we'll have pressure. This mole Kelvin is going to be bad at the bottom. And then we got 300 or 298 Kelvin. Oops. Divided by a pressure of 0.980. atmospheres. So now when we look at this, again, just plugging it in, we can do that on our calculator pretty easily. But now if we look at the units here, we've got mole, and then in the gas constant, we have mole in the bottom. Those are going to cancel. Same thing with the temperature unit, Kelvin cancels. And now the unit on top is literally liter times atmosphere. We already have atmosphere in the bottom, so that's why our only unit now is just going to be liters. So when we actually go through and plug all this in, oops, let me erase this. The work that they're showing there is exactly the same thing we had up till that point, so we can see the same thing. Just erase this. Yeah, so you can see 40.8 moles, the R for the gas constant, temperature. And then the pressure here. So in this case, it's showing liter atmosphere, and then it's got mole inverse 1, -1, Kelvin -1. So it's really the inverse of those. So they're still showing per mole per Kelvin. That's why it cancels. But ultimately, we're just left with liters. That's why it's going to be our final unit there, is in liters. So if you want to practice with the second one, feel free to go ahead and do so. And then with the next video, we'll just have a bit more practice with this. We'll start seeing how we can apply this to chemical reactions as well.